Jenny was one of the early inventions of a mechanical machine that is used to produce textiles. And subsequently, in 1764, a steam engine called a Newcomen steam engine was used by utilizing the power of steam to have a linear reciprocate motion to be translated for pumping or oil or water purpose applications. And this engine was one of the most inefficient machines where there was a lot of steam lost because of the way it was designed. And James Watt was actually working as instrumentation technician who was called into reduce the steam wastage and improve the equipment. And he, after fixing this, he realized that a new machine can be designed, and he designed his steam engine, which basically converted a reciprocate motion to a rotary motion. So that actually had enabled the revolution called first industrial revolution. So this was used to massively automate factories, create engines for railways or locomotive and so on. Prior to that, we used windmill farms, windmills to have some of the industries, and there were limitations of such windmills because they could be located only where plenty of wind is available. So this is actually one of the machines, replicated and retained in Brazil. And this is actually the cylinder, and this cylinder goes to a lever, and the lever actually connected to a wheel that actually rotates. So the steam is periodically loaded and unloaded into this chamber, and that energy was converted into the steam machine. And that was actually marked one of the first industrial revolutions. The second industrial revolution was marked by the invention of electricity. And the scientist who contributed one of the earliest or foundational inventions was Michael Faraday in 1800s, early 1800s. So he invented the relationship between magnetism and electricity. He invented the mechanism to generate electricity, as well as create what is it called a motor by flowing current in the presence of magnetic field. Subsequently, that was radicalized into real world applications by many great scientists, some of who are actually shown here. This was Nikola Tesla, who actually pioneered the AC generation and distribution, and Thomas Alva Edison, who actually pioneered DC based power distribution systems, as well as the invention called bulb. So in fact, there are so many people who contributed to this, but collectively the invention of electricity radically transformed the industrial way, as well as human life in the world. Okay. Now, as I mentioned earlier, every such a change is called a revolution because of radicalization. So, what all the physical equipments like the steam engines in many applications were converted to motor-driven devices, and lighting itself made a different aspect for the human life. And the third revolution, industrial revolution, was actually enabled by inventions by electronics, computers, and information technology. In fact, there were many inventions soon came out. We can see this happened in early 1900s. And by the middle of 1900s, we had several more inventions coming up with starting early from the vacuum diodes to vacuum triodes to semiconductor based transistors, and from the semiconductor based transistors to computers and associated theory called information theory and technology. So this actually has revolutionized the aspect of many of the mechanical devices or many of the electrical devices into electronic devices. And one very important invention in this domain was actually called the amplifier, which was due to the invention of the vacuum triode, or what was called the transistor, subsequently in its semiconductor variant. So this amplifier made a very big contribution to human civilization, because many of the real world phenomenon had signals which are very, very weak. And the magical device called amplifier could actually transform that into much higher power output, and that's because of the device called transistor, which has a capability to have a large current converted controlled or modulated by a small current. And this large current could actually be varied by the small current. That actually made a huge invention in many applications, in power electronics, in communications, in audio systems, and so on. Now, the evolution, once the electronic components are transferred into ICs, they were made into computers and so on. The computer generation started as part of the third industrial generation, where the early computers were using vacuum tubes. The early computers like Enigma, which was used for encoding or encrypting data, and the antidote to that called Colossus, which was actually to decrypt the German encoded data. And all these are actually examples of the early vacuum tube computers. One of the very notable and very path-breaking innovation was the invention of the computer called the electronic numeral integrator and computer ENIAC, which was built in the middle of the 1900s, and which involved like 18,000 vacuum tubes with 1,500 relays, occupying an area of 167 square meters, weighing the whole thing about 30 tons. And more importantly, it consumed a huge amount of electricity, which is actually today useful for several of the colleges together. Not even just a single lab or single building or single institute, but maybe multiple institutions can run with this amount of electricity. So this is one of the very important milestones of computing industry or computers, and that led to further refinements, further standardizations, and more clearly defined models, such as the von Neumann model of computing, which is called IAS architecture machine. So IAS stands for Institute of Advanced Studies, and which subsequently becoming like the most popular stored program computer architectural von Neumann architecture. So this is one of the pictures of the ENIAC, which was recently resurrected and maintained as a museum piece. Now, as I mentioned earlier, with the vacuum tube itself, we had developed computers that could make a lot of computing purposes. Subsequently, when vacuum tubes were replaced by transistors, we could make computers which are very fast, very cheap, and we could have new kind of media, scalable media with the punched papers or punched cards. Outputs could be printed out. In the vacuum tube world, we were able to give input through switches or input through gears, whereas output was also seen through some sort of lights or even some sort of gear positions and so on. Whereas that input and output devices were replaced with much more comfortable, much more scalable input-output mechanisms. So memory also was replaced from the original magnetic memory to electronic memory using transistors. The instructions set could be expanded, instruction size could be expanded, program size could be expanded, and new languages were developed, high-level languages developed, because there is a need for large number of applications to be developed that can be run on a computer. Now, subsequently in the same century, 1900s, we found that the integrated circuits came into existence. Miniaturization became much more important, and more importantly, the single board microprocessors or CPU on a single chip. Okay, so that was actually another revolution that came into existence in the form of 808, 8008, 8085, 8086, and so on. So this is a generalization, because before that we had different circuits. So circuit 1 for one particular purpose, circuit 2 for another purpose, circuit 3 for a different purpose, and so on. So these all generalized into one single CPU, which could do all the purposes of circuits, something in addition, multiplication, subtraction, everything, with a programming instruction that could manipulate the operations of the microprocessor. So that resulted in rapid evolution of the computers. further aided by fourth generation VLSI, where millions or thousands of chips, a single chip could be done. We had now made a big progress into computers, and we required the need for computers to interconnect themselves. Okay, and within the organizations we had what is called computer networks, where people could communicate among the computers. But then across organizations, it was not possible for a long time. Then subsequently people realized that it's a good idea to connect the networks, and there came the internet. And that actually led to the fourth generation, where the Industry 4.0, which is said to be going right around all of us in the form of Internet of Things, with the services aided by artificial intelligence, and a lot of applications in the robotics world. And collectively, they have this cyber physical interaction system. So these revolutions, from the first industrial revolution aided by steam engine, had many innovative or radical changes in mechanization, automation, factories, transportation, and so on. And similar radical improvement happened because of the electricity and its applications. And from there, from the electronics, IT and computers had an equally big or even more radical changes. And now we are in the middle of this Industry 4.0, which is actually unleashed right in front of us. So what actually is, what is important here, one of the important aspects is that, the word that I periodically mention as reinvention. Okay. So reinvention, referring to the process of inventing everything that was existing in the prior industrial revolution to suit the modernization, to benefit from the current technology in the current industrial revolution. So, for example, you have seen, many electrical equipments in the Industrial Revolution 3. In fact, this kind of reinvention happened in all the prior revolutions too. Okay, for example, here it was a locomotive which was actually running on a steam engine, that was actually translated to electrical powered locomotive. This was existing. Now it is getting reinvented in a different way in Industry 4.0. Okay, with electronics came in, all the automotive vehicles came with the computer-driven, embedded automobiles. Now it's actually automated drivers and so autonomous vehicles and so on. So you can see the locomotive that was once driven by steam engine, later driven by electrical power with the electricity, and which are subsequently made into computer embedded automobiles, are now becoming IoT driven automobiles with the autonomous operations with the AI driven vehicles. And so this is a reinvention process. Now, if you look at another aspect, so let's say that electrical bulbs. Electrical bulbs are actually inventions happened in the second industrial revolution. That is actually improvised with the incandescent lamp to fluorescent lamp to LED lamps and so on. But if you see, LED lamps came into existence in this industrial revolution 3. But now it is getting reinvented as IoT enabled bulbs. Okay, IoT enabled bulbs. Or if you can see a fan here, fan was actually a mechanical fan in the Industrial Revolution 1. It is actually made an electrical fan as part of, it is reinvented as electrical fan in the Industrial Revolution 2, and which was actually made with the electronic controls and so on, with the same electrical thing. Now what is now getting an IoT enabled fan. Okay, and many things like that. We can say motor. See, motor was actually a steam engine driven motor here, and that was made an electrical motor here. Okay, and this is actually now reinvented as IoT enabled motor. So what that means is everything that we have done in the Industrial Revolution 1.0 or updated as again reinvented as Industrial Revolution 2.0 technology to what is required for Industrial Revolution 3 is now getting reinvented as suitable, modified, improved, more capable device to suit the Industrial Revolution 4.0. So everything is actually getting reinvented to seemingly very simple things. As you know, some of the examples that I will show, the keyword for Industrial Revolution 1.0 in one perspective. Okay, there are Industrial 4.0 is actually reinvention. Okay. So even though this was present in prior industrial revolutions, today it is becoming much more significant, much more prevalent, omnipresent, and much more important. And this is an opportunity for every one of us. So we can see that this is actually a pen, which was an ordinary pen in the old industrial revolution, maybe 1.0. This was existing, and it may have some improvements, and now it is actually in Industry Revolution 4.0 as a IoT pen. Okay, so this was, I mentioned earlier, it was actually evolved in Industrial Revolution 2.0, then it got improved in Industrial Revolution 3.0, and now in Industrial Revolution 4.0 this is an IoT enabled bulb. Okay, so this was actually a speaker. I would say that this came into existence in Industrial Revolution 2.0. Maybe it was improved further, reinvented on Industrial Revolution 3.0. Now it is facing a significant reinvention in Industrial Revolution 4.0. So to say, in fact, I have shown one picture, but it's a representative picture of a typical IoT-enabled speaker that is produced by some of the major players. Okay. And this actually involves not just the inventions from the past generations, many new inventions too. One example is that it actually has a capability to have signal processing, AI, communication, networking, and IoT capability, and above all, it actually have a context awareness capability. So one very interesting capability I have found in some of the such industry enabled or IoT enabled speakers is actually there are multiple microphones or multiple speaker elements existing in that. So by careful design of this AI and signal processing capability together, this actually gets very significant new capabilities. Like, for example, if a person is actually standing in this side of the room, then they collectively work as a beamforming device to identify the person's location, listen to him better. And if the person is actually listening from some other direction, then the voice produced or sound produced, music played by will be focused to that particular direction. So it is able to locate the person within a room and respond to his needs in a much better way than other speakers or other localization technologies can do. So similarly, this was a wall socket in Industrial Revolution 2.0, and probably slightly improved Industrial Revolution 3.0, and radically improved in Industrial Revolution 4.0 with the internet connectivity. It is able to do control capability, switch on, off, maybe voltage control, current control, and monitoring capability, and all these capabilities are actually built into this particular device. Even ordinary switch like this is actually getting reinvented. So it's not just limited to this, and the entire aspect of human life is getting transformed in this kind of reinvention of articles. Okay, some of these are actually opening up a very significant market space. For example, this particular sports goods. So whether you have athletic, gymnastics, or other games, So you have so much of opportunity, and companies are actually tapping into significant research, development, intellectual property rights opportunities in this space. For example, depending on the kind of sports activities you do, everything that is traditionally used is getting reinvented. So watches are reinvented, wristbands are reinvented, shirts are getting reinvented, socks, shoes, even shoe sole is getting reinvented now to suit the needs of this particular emerging industry scenario. So it's not just that, even undergarments are actually getting reinvented. Skipping rope is getting reinvented. So the reinvention opportunity was limited in the prior industrial revolutions, but here the reinvention opportunities are mind-boggling, and that is actually a very good opportunity for every faculty member who is attending this lecture and every student who is actually going to be trained by these faculty members. Now, one of the difficult situations that faced by the Internet of Things enabling of older technologies, older devices, or older installation was that they were already there in the practice. Say if you have a window in your home, window is already there, and you cannot actually replace the window with a new Internet of Things enabled window. So that's why new kind of inventions, which are very simple inventions, but still serving a big need for the emerging scenario by having retrofitting the things in your home. So retrofitting can be done by appropriate, suitable, minor, simple modifications to existing ones. So in fact, this is actually an IoT enabled motor. Okay, this IoT enabled motor is actually retrofitted to a window blinds. So this is actually window blinds, and these window blinds can be somewhat controlled or monitored by having this retrofitting kit attached to it. So you can also see this. This was actually industrial revolution 2.0 lamp, table lamp, and this table lamp can be converted to a limited extent to industrial revolution 4.0 enabled device by having this what is it called, an IoT motor and actuator. Okay, so you will be able to do some kind of control on off like control thing too. Okay, but much more complicated devices are available. This is, in fact, this is also an IoT motor which is customized to actually drive a knob. This knob is actually this was a traditional knob. Inside the part of it's a traditional knob, and outside is actually an attachment with a gear. Okay, gear teeth attachment. So that actually can be controlled by this IoT motor, and you will be able to control the temperature of your thermostat by doing that. So this is one example of the retrofitting. In fact, there are several devices which are traditional industrial revolution 2.0 or 3.0 devices that can actually be controlled. So this company called Hanke Design actually have come up with what is it called a smart knob or a digital knob. So this digital knob is something like, so imagine this is an electronic device or electrical device which had certain kind of knobs, and these knobs were mechanical knobs. You can turn to choose a particular voltage, current, or position or time so that the electronic or electrical device will work. And this particular knob can sit exactly the same place by replacing that. And this knob is actually an IoT enabled knob, which is able to control as well as monitor using a mobile app or IoT based application. So traditional devices can be retrofitted to make it ready to be interacting with the new applications or new services or new IoT enabled IR4 scenario. So that is actually becoming very relevant. It's a very recent phenomenon to have this retrofitting devices, because there is a huge market that can be potentially do. So this picture is actually from a company called Libelium. Libelium produces sensors, IoT devices, and so on. They also produce single board computers, chipsets, and so on. So they come up with this representation picture that shows the spectrum of applications from marine transportation to marine transportation to the agriculture to industrial transportation to urban living. So every spectrum of our life is actually getting touched by this revolution, unlike the prior revolutions. Prior revolution also had significance, but unlike anything that we have seen before, this is actually going to be very relevant. And so the applications are actually driving. And one very important dimension that I used to explain in my lectures is actually just the smart home application itself. Smart home is actually one of the important applications of IoT, one of the important applications of Industrial Revolution 4.0. And this itself is actually going to show you the power of IoT in various areas. Okay, now let me just show one example. If you have not already heard this particular point, let me take one segment. If you take any segment here, this is a bedroom, this is actually a living room, or this is bathroom, or this is a kitchen plus dining, and this is the entertainment media room, garage, or office room, and whatever. You take any example. No, I don't want to tell multiple examples here, just to pick one example. So let me just pick this, say maybe this bathroom example is one of the least bothered example in the whole space in the Internet of Things. Okay, so if you consider this particular bathroom alone, so you are actually going to see a lot of technological transformation because of this IR4. Okay, the reason is that this is actually going to be a smart bathroom, whether you realize it or not. Okay, the smart bathroom can be retrofitted or fitted with the smart IoT enabled devices, so it is actually going to work as a a lab for your healthcare needs. The moment you step into the bathroom, it is able to measure your body mass index, and it will tell you whether you are actually healthy or not. How is the trend on your BMI? That the bathroom will tell you. Whether you are going to exceed the threshold of obesity, that your bathroom will tell you. And even your bathroom, after measuring your progress of health, it might even appoint a doctor's request. It might even alert your insurance. It might even request some kind of a hospital visit or whatever. So you might not realize what the bathroom is doing to you, but it's actually going to give you a significant health healthcare support in the future. And it can actually do with some sort of sensor attached to it. It can actually do the chemical analysis, and it can tell you whether you are susceptible for some of the diseases. So it actually takes care of a lot more aspect than this. In fact, there are several companies that have actually made these devices like wash basin, the shower, and other plumbing articles to be internet enabled. There are the whole infrastructure is actually getting controlled by what is it called, an intelligent controller. Okay, this intelligent controller is actually an IoT enabled device. This actually gets controlled by your mobile phone or your internet device or whatever. And in fact, if there are multiple users of a home, everybody has a profile of what temperature they set for the shower, what amount of water they actually use it, and all these profiles can be loaded as soon as you enter into your bathroom. The bathroom actually realizes that you have come in, and it should be ready for you, and it should be working. In fact, Kohler is one company that actually had made many of these plumbing articles, which is traditionally IR 2.0 or IR 1.0 devices, which are now made IR 4.0 ready, and to do that. So this segment, this itself is going to be a very new market segment. Same with every other room that you consider, that is actually going to face a lot of technological revolutions, which many inventions are yet to come, or there is possibility exists. So you might have heard the stories about this garage where your car is coming, and this car is more likely to be a computer autonomous controlled, and it's going to be an electrical vehicle, and the car is actually going to not only get charged but also get diagnosed for any of the potential issues. Sometimes, some of these cars can have computers that can actually be running for 4 to 5 hours of diagnostic checks. Some of the Toyota cars, even in the older versions, they will have a diagnostics that can take like 4 or 5 hours. So it undergoes a mechanical health check, it undergoes a software update, it undertakes recharging of the power battery. So all these are actually capabilities that are going to this particular segment of the room called your garage. So that way, if you see that every room in this particular smartphone, so there is a whole new segment of technology market that is actually going to be developed, and that is actually a big opportunity for the coming years. So I have done a very quick survey recently on where are we standing, because IoT has been in talks for the last 4 or 5 years, and we want to see in 2021 where we are standing. And this is actually a survey conducted by a company called Farnell in UK that actually made a very recent survey from the engineers. This is not a market survey, this is an engineer survey. So people asked questions to engineers, what are the most important aspects, and they concerned that security is one of the very, very important aspect. Reliability of communication is another important aspect. The ecosystem of the IoT is actually a very, very important aspect of that. Then most important concern still remaining as a security concern. So this demands, there will be a lot more requirement for engineers who might want to do security related degrees or programs or projects, because there is a growing need for this particular area. Okay, connectivity is very, very important area, with the 27% of engineers commented that it's very important. Interoperability, because of the lack of standards, as you may have seen that Alexa has developed their own proprietary suite of communication protocols and technologies, APIs and so on. Now Google Nest has developed something else. Every company is developing non-interoperable proprietary technologies where interoperability is actually a question. In the days to come, it should emerge in some form. So what is the most important industry? That is Industry 4.0, where we have not discussed that industrial automation is actually one of the very, very important application for IoT. Home automation is actually the second important industry. AI applications, smart cities, and so on. Even if you consider energy efficiency or energy management is a very, very important area for communication. You can see, if you see the worldwide market for energy management, you can see not many countries have utilized it. Even in the advanced countries, only small number of countries have become popular with energy management using IoT. So that actually tells you in this particular segment itself, there is lot more new devices and applications will be required. Healthcare is one of the very, very fast emerging areas, very important areas. That is a very small area compared to other areas in this particular survey as it emerges. But in the years to come, this 8% might even shoot up because of the COVID-related issues. Now, when we looked at what are the causes of slow growth, as I mentioned earlier, last 5-10 years, people have been talking about industrial IoT, but we have not seen that kind of automations. What actually prompted that kind of lack of rapid growth? Of course, rapid growth may not be possible, but many people mentioned concerns over data security is a valid issue. Lack of business strategy is the second biggest concern for growth, and technology limitations or difficulty to retrofit. Retrofitting has become a keyword very recently, and new devices, very, very small companies started producing retrofitting items, and this word is actually coming as a relevant word today. Okay, then what kind of return I can expect from the investment? That concern is actually giving, and there are many such in fact inadequate software applications. So in fact, all these are actually giving you opportunities for developing new technologies. So what kind of businesses can benefit from IoT? So most important kind of business is actually manufacturing and data analysis companies, operation applications, and so on. Then which programming languages are used for IoT development? This is from the perspective of engineers only. C, C++ is a still dominant language platform. Python is second most important. Even though C, C++ platforms were existing for a long time now, they are still widely used because of the efficiency in working with embedded systems. Now, what kind of connectivity are used for IoT related things? 66% said that Wi-Fi is actually the preferred connectivity, first choice connectivity. 40% said that first choice is actually cellular network connectivity, and so on. And whereas when it comes to wired connectivity, Ethernet is actually the major player with a very, very significant number of applications used Ethernet connectivity. Now, out of the many popular boards available, which single board computers are available or used in IoT designs by the engineering community. Raspberry Pi actually is a leader in that area with the Arduino. BeagleBoards, lack significantly low, and the company who did survey is actually part of Avnet, which produced this 3% of preferred IoT design boards. Now, cloud is becoming very relevant, and in fact, it has already become very relevant for IoT space too, because most of the IoT developed data is actually getting repositorized in the cloud and getting processed in the cloud and so on. So major players like Amazon, Google, and IBM all trying to utilize this particular segment, cloud for IoT business. But still, majority of the people are actually trying to use a personal cloud solution where the consolidation by major players like Amazon Web Services or Google Cloud Platform or Microsoft Azure will be significant. So this space is actually a fragmented space where everybody prefers to use a different personal cloud solution. And you can see Amazon was not exploiting this market until like 4 or 5 years before, where they were focusing on traditional web-based cloud services. But now IoT cloud services are becoming relevant too. So 1/5 of IoT cloud market is actually with Amazon, and 1/5, another 1/5 is with the Google, and roughly with Microsoft. You can see major players are actually trying to buy this particular IoT cloud market too. So the capability to attach sense or capability of sensing can also be different. Most of the applications involve environmental sensing still, motion sensing or visual sensing or other 10. You can see that the health monitoring is a very big application, but still it's a very, very small compared to other kind of applications. Now the market growth, again, this is actually a review of the past things, because we have seen several such reviews, but what is the current situation? So this review is done by a market analytics agency called Modern Intelligence. So the global IoT market is now going to reach about $1.3 trillion by 2026 from the current $0.7 trillion. So this is actually giving 10.5% annual growth. So this is actually very big growth, very sustained growth even today, because we were actually expecting the last 4 years, in fact, and if I remember the 2015 survey, this was expecting to grow something like 20 to 25% growth to where we had. In fact, there was a COVID period that slowed down the space, but still this growth is, even though the market has grown up significantly with the 761 billion, this is a very huge market, and the growth is still very, very solid with the 10% per annum. Now, the number of active connections over cellular network, cellular networks are now becoming relevant for IoT, because they have a separate narrowband IoT traffic scheme, where they have new plans for allowing IoT customers, say maybe 500 MB data over 10 years at something like €5, €5 at such a low cost for such a large volume for a very long period. This is an example traffic or example billing pattern that was allowed by one of the players in the Europe. So this kind of new traffic schemes, new billing schemes, new pricing policies are developed for cellular networks, and as a result, Internet of Things devices are using the cellular infrastructure, and this is actually very small percentage of devices that people expect by 2025 in Europe. 3.09 million connections will exist over the cellular infrastructure. Now, you must have seen that the previous data I have shown, many of the users are still preferring Wi-Fi. Okay, cellular network is not preferred as that is not the best option. It's actually second option only, 5G, 4G, LTE. Many people are still preferring Wi-Fi, but this itself is a very rapidly growing market, even in countries like in India. Okay, so this shows that in the future there will be significant more devices that will be connected to the cellular infrastructure from IoT. Now, if the world is divided into 3-4 regions in terms of this IoT market growth in the next 5 years, okay, so this is how the picture is, where the high growth areas are actually marked in green color. Fortunately, India is actually in the high growth area. So what this high growth means is the opportunities to embrace this new technologies for IR4 is very much prevalent for us. So this is actually going to be an opportunity compared to other areas like the US, which is actually growing at a medium rate, and the other countries are actually growing at a lower pace. So now this is why I'm actually encouraging all the institutions and faculty members to ask you this question. Now, have you developed any intellectual property, any IPR in the area of Internet of Things or Industrial Revolution 4.0? Okay, if you have not done, then this is the time to do that. So if you say, no, I have not done, okay, this is the truth, then this is the time that you have to start. Okay. Now, second thing, have your institute, your college or institute developed any IPR office? If you have the answer yes or no, if it is no, okay, then you have to start now. If it is no, you have to start now. You have to do that. Okay. Now, how many of your students are trained to get employed in Industrial Revolution 4.0? Okay. So if this number is low, now you have to take a decision. You have to engage them in many more projects. You have to actually encourage them to create a fundamental or intellectual property or patents or copyrights in this domain. That is actually a very important requirement for you, because as I see that the opportunities as a faculty member or as an opportunity as an institute administrator is significant during this next 2021 to 2025 or even to 2030. So this time is very significant in your career, and you have to make a significant mark. And this IoT enabled Industrial Revolution 4.0 is a major direction for you to make an impact. Okay, so as I mentioned earlier, the pictures I have shown you in two, this is actually a story, a big story, not a single story. It's a collection of large number of stories where inventions can be thrived for every corner of this house. And so every aspect of the human life in this spectrum, you can have an impact. So that opportunity is now with you, and you should not miss that. Now, second reason why I am saying this is very important is because the survey also shows the dominant players in the IoT market. In fact, when I gave a lecture on 5 years back on this particular topic, we didn't have these major players present in that, all small players only. So if you see the market significance from fragmented space, which means very small players, to to consolidated stage where major players only play, like operating system market. There are only major players, and you cannot start an operating system and make a big impact that easily. Okay, so IoT in 5 years back, it was actually here. Okay, it was here 5 years back. And in the last 5 years, it actually emerged to this particular area. So today, if it is here, where with some kind of major players and a significant number of minor players exist in the market, but it will, in the long run, it will actually become a consolidated market to only major players present there. Okay, because their products will dominate the market and it will be hard. So this is what is your opportunity. You are now here. This is actually your opportunity, and many big players will be later acquiring companies in this particular area, because this fragmented market is actually becoming very fluid environment for you to innovate and win. So the biggest player as of now is Cisco Systems, with Google becoming second only, IBM Corporation, Microsoft Corporation, Huawei Technologies, and so on. Now, if you remember, these are the 5 major players. There are so many other significant players exist. For example, Samsung is actually a player who actually have significant stake in this. Samsung has applications, devices, and so on that can be controlled. Then there are many other players. In fact, Amazon is a very big player. Amazon is not in this list. So you can see the number of significant players is actually limited even today, but maybe 5-10 years down the line, the market will be consolidated. And this fluid chance, you should keep opportunity to be grabbed. This is, as I mentioned earlier, this fluid state at this point should be utilized. Now, again, this architectural developments for this IoT area is very somewhat open area. There are innovation possibilities, but companies try to develop their own architecture. So I will just briefly discuss the architectural possibilities for IoT and what the companies are thinking of in terms of this architecture, and what IEEE is thinking about in terms of architecture, but it's still a research topic. Now, one of the early academic representation of the architecture for IoT is actually this 3-layer architecture, which consists of 1, the perception layer, 2, the network layer, and 3, the application layer. The perception layer, as the name represents, it is actually the sensing layer. Okay, it senses the ambience and make a sense of what is happening in the environment. And this network layer is actually that internet layer or the communication layer. And the application layer is where the data is used for some kind of application. So this was one of the earliest applications or earliest architectures of that. It had limitations in the sense that the true IoT capability was not exploited by this particular architecture. So the true IoT capabilities could be exploited with modified IoT architectures, which again consists of 3 layers, but the bottom layer has been modified to have additional capabilities. So this layer is better called cyber physical interface layer, because it not only does the sensing activity, but also does actuation of or acting on the physical world. So that's the reason why it's called a cyber physical infrastructure or cyber physical interaction layer. The second layer, the internet layer, consists of the entire internet protocol stack. As I mentioned earlier, the internet protocol stack has layer 1 physical layer, layer 2 data link layer, layer 3 network layer, and layer 4 transport layer. It also has an application layer, that is layer 5, and this is an optional layer for IoT layer, but these are actually mandatory layers for IoT network layer, and this is optional. In some cases, we also have application layer, which is part of the internet layer, and so this allows us to communicate with from the device to the cloud, or from the device to other device, and so on. Now, the third layer of the IoT protocol stack is actually the application artificial intelligence layer, which deals with analyzing the data, creating in business intelligence, and by using AI and machine learning techniques, and also gives interface for the rest of the world to access the IoT system. So this is much more mature architecture, which can capture the essence of the whole IoT concept, and which can also capture the essence of the whole IR4 concept and so on. So, but now companies have come up with their own proprietary architectures, and they started deploying systems and so on. This is actually an architectural representation of Cisco's IoT system, where the layer 1, again, they have like 7 layers. Level 1 or layer 1 is actually the collection of physical devices and controllers, which include sensors, machines, devices, intelligent edge nodes of whatever type. And the second layer is actually the equivalent to the internet layer of the previous 3-layer architecture I have mentioned, where the connectivity, communication, processing are actually dealt with. And the third layer, which means all the internet protocol stack is, say TCP/IP stack is actually involved in this layer 2. The third layer is actually edge computing layer, which is analyzing the data or processing the data very close to the end device or very close to the edge of the network, so that latency advantages may be there. Now, the fourth layer was actually data accumulation or storage layer, which usually is done at the cloud. This is an edge-like activity, and this is a cloud activity where the storage space will be cheaper and available in large quantity. Now, layer 5 through 7 are actually data processing or data analysis or data reporting or user interface levels, where layer 5 is dealing with the data abstraction, where it is aggregated as well as allowed for access, and application layer 6, which involves the reporting, conducting the business analytics as well as taking control decisions. And the last layer is actually where the people or user interfaces, APIs and so on to do that. So Cisco's one of the major players, as you have already seen from the data that I have shown. The Oracle IoT architecture is slightly different with a different perspective. So this again has lowest level having devices. You can see the devices with RFIDs or ATM machines or vehicles, refrigerator, shopping carts, or other electronic gadgets and so on. So these devices will be having their own appropriate gateways that can talk through a service provider to a cloud infrastructure where the rest of the layers will work. So this is actually the network layer, as I have mentioned earlier. This is where the internet protocol stack is running. The whole infrastructure this layer will actually provide the communication or networking resources. So at the cloud side, so you have different layers as per the Oracle IoT architecture. One is actually the infrastructure services. The infrastructure service is actually maintaining the underlying device infrastructure. So, for example, devices that can be managed, or the connectivity among the devices, or representation of the data from the devices. So that is actually managed at this level. And above this level, there is a special layer called IoT services layer. So depending on the kind of services that you need, different kinds of services are defined and implemented, such as event processing service, integration of data, security services, identity management or user interface or big data analytics. Even in fact, this analytics on top of this infrastructure is actually defined as certain services. So it's easy for the users or developer community to utilize this service or use a combination of this service so that they can develop new additional services. So for example, this IoT, the developer services can actually use a combination of IoT services so that they can provide a new kind of services. For example, this third-party APIs developed by a developer community can involve a combination of security services access as well as big data analytics access. So they provide these two together as a new set of APIs so that the user can actually use this enhanced set of API. So that way they actually allow innovation in a significant way as part of this IoT developer services. And on top of this, you get the applications which is actually growing, like the software development applications of today. like how you and I develop, various applications for Windows, Microsoft Windows or Android, or even Apple Mac. IoT applications are actually growing. This is a very emerging market. So you create a different kind of application services that will work in an intelligent way on this large volume of devices. Now, IBM IBM is also a major player, even though compared to the market of Cisco and others, it may not be very big. Now, let me explain this briefly. When they have represented this in a very, very complicated way. So, IoT, so IBM focuses on industrial IoT platform. So, IIoT platform. Actually, that is represented the core or the centerpiece of their IoT architecture. Okay. So, this centerpiece is actually shaded here in a color. So, you can see that here. So, now you have the end devices that is here. So this, if you can look at here, this is a sensor and actuator attached to the physical entity. Okay, so you are, this is a door or a window or a refrigerator or whatever physical entity is it, or it's a pot of plant, or just a wall, or whatever is a physical entity. So you have this sensor actuator embedded into that will be eventually connected to an embedded platform that is nothing but the device. So this is a device, and it has some firmware, aggregation, network connection, some protocol stack, and so on in this embedded device. So this is actually the sensor part, or what we call as the end device. So this left side of this is actually the end device. Okay. Now the whole thing from here to the network is actually called the edge of the whole system. Now, the sensor either takes periodic data, processes it, and forwards to the proximity network, or take instructions from the proximity network and act on these actuators here. So it does whatever is expected from the embedded thing. Okay. Now, the proximity network here that you may be seeing here, that is actually interacting, allowing interaction between the device and the IoT gateway. So the IoT gateway is much like an Wi-Fi router or Bluetooth gateway or a cellular gateway device, which actually has a little bit more complicated protocol stack, because it has to serve several such devices or large number of such devices. Say maybe if you have a Wi-Fi access point, you may want to deal with the hundreds of devices in your home, or maybe thousands of devices in a small campus. Now, this interaction is actually marked here, and in some cases you have an edge computing module attached to the gateway or working or co-located with the gateway, or in some cases there's a separate access network that allows this gateway communication to a network device called an edge service infrastructure, edge services node. So this edge services node is very, very important, because you get some of the services much faster. So let me show you one example. This is actually a planned port. This is actually a plant which has some sensors and actuators. This is a smart port that you are installing in your home, and this has embedded devices and controller or computing device that you can communicate with your Wi-Fi router. This is your Wi-Fi router, and this Wi-Fi router connects to the internet and then to the cloud infrastructure managed by some sort of a company, and that company decides, company offers a new service that you may receive as a service on this plant's performance. So company may send some fertilizers through a different infrastructure. Maybe you have pipes attached to that, and fertilizer boxes are attached, and the fertilizer box will be filled in periodically by the subscription service of the company, and you get different plants at different times, or different fruits at different times, or different colors of flowers at different times, depending upon what the service offered by the company is. Now, this data sensed by this plant should be processed by the cloud infrastructure, and sometimes getting back the result is very low, very long which can take time. So what you do is an edge computing service here. So some of the services will be done, computation will be done by this edge computer, and the results will be sent back very quickly. So the access time here, it may be less than 1 millisecond because of the edge computer, but if you want to go all the way to the cloud and come back, then the service may be hundreds of milliseconds. So some of the decisions can be locally done by this edge computing service, and the platforms solutions approaches for edge computing is a very active research area now. Now you have whatever sensitive data has reached the edge device, and it is actually getting to the IoT platform. So IoT platform first deals with the connectivity and data brokering, and then this data has to be refined, managed into the into the clean data. Okay, so that has to be done through the data management processes here. You can see that data management services and IoT lake, data lake here. So that is actually doing series of data analysis and processing to refine the data in an easy way that other services can access. So one of the other important services is actually the AI analytics service that accesses the data from the IoT lake and gives it for various other applications, such as the application runtime, as well as visualization support, or user management, or device management application, or even the enterprise connectivity, as well as application data. Okay, so the enterprise applications will require this refined data learned and applied by this AI techniques to this enterprise resource management. So that is roughly the representation of architecture planned by IBM for this. Then there are different architectures by ITU. ITU is International Telecommunications Union. They came up with their architecture, and then IEEE has recently made 2019 made one architecture, which is one of the very relevant architectures, because it deals with an architectural framework for IoT, where you have one IoT abstract domain. This is actually a conceptual model of a generic IoT infrastructure, but this generic IoT infrastructure has limitations when it is applied into specific IoT cases. So they identify so many specific cases. One of the specific case of IoT architecture is smart buildings, second smart grids, third smart manufacturing, fourth intelligent transportation, fifth smart cities, sixth healthcare. So when it comes to the architecture, this generic architecture has limitations in implying in every scenario in an efficient manner. So you need to have specific architecture. So the reason is because smart buildings have different aspects compared to smart grid, or these two may have different aspects compared to an intelligent transportation infrastructure or even a smart city. So healthcare case will have different type of sensors, different type of data formats, different type of services that should be carried out, and so on. So the architecture has to be different. So this tells the opportunity to have application specific architectures, which are very important. As you may be able to see this example, IEEE 2413 started mentioning about smart cities. So when it comes to the smart city ICT infrastructure architecture, they come up with a devices level, a networks layer, to cloud layer, to platforms layer, to applications layer. So you can see the sensors involved in this particular architecture are specific to the smart city case. So sensors for environment, sensors for the camera, some of the users, even the utility equipments of the city, the vehicles of the city. So these are the sensors. But if you see that this might be very different from other applications such as healthcare. Now, communication layer or the network layer is actually the second layer in this architectural variation of IEEE, which involves the city's communication network or city's IoT network, or whatever network infrastructure they give. Sometimes this may be like the, as I mentioned earlier, cellular network infrastructure, or Wi-Fi network deployed in the entire city, or the wireless mesh network deployed in the entire city, or even city may have their own IoT network deployed by using the technologies like LoRa or Sigfox, which are customized network for IoT service. Very long range. These are very long range, very low power, very low data rate networks. Very long range, very low power, and very low data rate networks. But it is very low cost to set it up. So the whole city, in fact, for example, the city of Trivandrum or city of Cochin can set up, the municipality or corporation can set up their own network infrastructure at a very low cost to serve for these sensors. But only thing is, when you have a very low power and low data rate network, some of these sensors cannot be supported because these need a very high data rate. This is high data rate, and whereas these are low data rate, and these are also low data rate services. Okay, so this is again high data rate service. User terminal also may have high data rate. So some of these low data rate services like sensors, this utility meters can actually be supported by an infrastructure deployed by the city itself. Whereas these high data rate, high data rate requirements might need something like a Wi-Fi or wireless mesh network infrastructure. It may not be possible even with the narrowband IoT kind of cellular structure. So that way, it can differ the networks that will be available for an ICT infrastructure. And the cloud data center is as typical in an internet data centers and the applications. Now look at the applications that can be differing, okay, from application to application, because you see the examples of smart government, safe city, smart campus, or even some of the command centers for disaster response and so on can be an application for this particular city, smart city kind of IoT application. So that tells the whole infrastructure of how the city is managed is going to be changed. Okay, and to tell you this law enforcement, law and order. Okay, just 1 week back, I just read one incident where there was a crime that has happened in the city of Trichy. Okay, so they have got some vehicle, that is usually said to be carrying out a crime and going through, and they wanted to transport, they want to identify the vehicle. Actually, this vehicle I exactly don't remember, but they found a vehicle involved in the crime, and they wanted to capture this. And what they have done is they got some details of this vehicle and passed on to the cameras in the city. Okay, passed on to the policemen manning the cameras in the city, and they kept tracing this until they found that this is kept nearby a hotel. Okay, so then police could straight away go there and arrest him right after the incident. So that's because of the connected set of cameras that could actually use to trace a person's movement through the city. Okay, now it may issue a lot of personal or privacy issues, but for the law enforcement, this is a significant deviation from the past, where usually they used to send a jeep with a set of policemen to capture this. Okay, to capture this person, trace him, follow him at very, very high speeds. But that tracing of a person's movement is now done through a city dashboard in a very crude way, done in Trichy just 1 week back. So this is actually going to be a big transformation in how law enforcement is done, how the management of cities affairs is done, how decision making is done, and so on. So that is actually showing the revolution that you are going to anticipate in the future. Now, let me show one more architectural deviation, which I said earlier as a very, very important thing, which is the process industry or manufacturing industry, where the internet is actually, Internet of Things is becoming the Internet of robotic things. So you can see their application or their architecture is different from the perspective of the devices. Like they deal with the physical layer of the devices, which are industrial products. Okay, And as you see, some of the industries can be very different from the other industries. So you can see the characteristics of the physical layer is very different. We can see the robots at the physical layer, or the robots can be different in their capability too. So the physical layer, the sensors or the cyber physical interface layer is a very different layer in this particular case, in the case of Internet robotic things. Communication layer might require very high bandwidth for many of the applications. The cloud layer, which is called processing layer, or the data storage layer, which are pretty much same as what we have seen in the other applications. But what differs in a very significant way is actually the services layer. So you can see lot more different services are required, services opportunities are available in this particular area. One example being this self-configuration or the orchestration of the devices. So you can see that in a process industry, the process involves raw materials converted from raw materials to finished goods, and the sequence of operations required by automated modules, say Robot 1, Robot 2, Robot 3, and programming of these robots to do a certain specific task is required. A raw material 1 to be processed into a finished product 1. Okay, now factory automation involves reconfiguration. When it comes to reconfiguration, so you may have to have very quick adaptation, and that's the reason why the orchestration layer is actually going to play a very, very big role. So maybe for the same raw material 1, so you may want to change from Robot 2 to Robot 1 to then Robot 3, you actually get what is called a finished product 2. So this change, the sequence, the process, the orientation, the programming of robots are now orchestrated so that you get a different finished product compared to the earlier one. So this is actually a process change that is carried out in a much rapid way compared to the prior industries or prior situations or prior industrial generation. So that way, you need to have new capabilities. This is not required for your city, or this is not required for a smart home, or this is not required for many other environments. But in an industrial environment, these kind of new services are required. So you can actually program the robot, program the sequences of operations, program their frequencies of movement of the raw materials or partially finished goods. So you may get different finished goods, and the system IoT of Internet of Robotics should be able to support that. So that way you will be able to do a lot more dynamic thing. So one of the recent emerging topics in IoT is called digital twins. Okay, digital twin. So this is nothing but there is a physical object. This is actually physical object ship, and digital twin deals with the digital replica. So this is actually a digital twin of the ship, and the internet being the center for allowing the interaction as well as management, control, and decision making process. So this is one of the very emerging directions. And it has very advantages. So another example, very popular example, is actually the physical oil rig or oil well platform, and it's a digital twin replica. Okay, very significant. You can actually, periodic observations are made from the physical world, and updates are made in the digital twin. Optimization decisions are taken in the digital twin, and the decisions are actually acted or controlled in this physical world too. Okay, so that way, the sensing of the real world and actuating back into the real world is actually mainly done by this particular thing. So the objective has many dimensions. Okay, one of the objective is to identify intolerable deviations from optimal conditions and in various directions. So such deviations can actually result in business optimization, or there is an error in the logic, or there's an opportunity for saving cost, and so on. So in essence, you can achieve greater efficiencies, and such decisions might even result in the action in the physical world too. So In fact, this is one of the evolutions that we have been doing in the past in various activities that we have been doing. For example, these mathematical models that we have studied, modeling the physical systems, like y is equal to f of x. You can take any value of x and see what is the impact of y. Y may be pressure of a system. X may be temperature of a system. So you will be able to find the extremes. For the extreme temperature, what should be the extreme pressure anticipated without actually applying the temperature. So you will be able to model a system mathematically and study the extremes without actually experiencing them in the physical world. So you can also find optimal operating points without actually having a physical system. So second approach we have evolved is at computer simulations. For example, you can create a very large network of thousands of nodes of a computer network and study the impact of a protocol, study the impact of mobility, study the impact of packet loss, fading, and other kind of real world situations without actually implementing them in real world. In fact, every time when we do some of the real world implementations, we simulate and see whether it works in the simulator before going the implementation. Okay, the third example is actually digital CAD models of mechanical objects. So you actually create a mechanical object in software using CAD model and see its operation, its extremes, whether it's feasible or not, whether are the pressure points, whether are the stress and strain points before going for actual fabrication. So the evolution of this into the next level is actually the digital twins, which gives a little bit much more capability to that. So the question is that why do we go for this kind of complications? That's because of the savings. There is, people have found that this is a study from McKinsey. McKinsey says 30% to 70% reduction in engineering cost and time can be accomplished with the digital twins. And material cost can be reduced. One another aspect they were very much interested is to have the labor hours reduced in capital expenses too. So in the operational expenses, you have a maintenance cost reduction 20 to 40%, higher production uptimes because it can prevent unplanned events, or you can actually reduce the manpower occupation in the industry, particularly in the risky industries such as oil rigs. People say that 30 to 100% of manpower reduction can be done with the digital twinning operation. Now, many other organizations say that they will implement a digital twin first and then evolve it over a time and apply right analytics and rules and then respond to business objectives too. So this company called Market and Markets Analytics say that by 2023 this market for digital twins will evolve to become $15.3 billion. So which means opportunities, which means jobs, which means employment for your students, which means research opportunities too. So let me just show you 2-3 variations of this digital twin processes. So this is one of the most basic thing, and this is actually dealing with the mechanical industry. The physical system is here, the digital twin is here. So you have the physical system. This is something like a large process industry system, which might be a collection of machines, which is infitted with a lot of sensors. And it also has actuators that can be controlled too. So that's a physical system which does some action, which does some processing, and that is infitted with the sensors. The sensors will take this data to communicate to the digital representation, where this data is used to replicate a digital replica. Okay, this digital replica may have a very, very complex software realization of the physical system. Okay, so this communication data is aggregated and analyzed, and system is modeled, the model is created, and on the model this analytics is created, which will produce insights. That insights is actually used to take actions, and these actions will be implemented through this actuators to the real system. So that way there is a loop from the physical world to the digital world, and there is a digital world to physical world communication for the actuation too that happens in this system. So Now, in real different systems, this is slightly different. So let me go a little bit faster here. So now, as I mentioned earlier, for IIoT architectures for digital twins, so that also has an architectural, platform for representing the data layer, where the production control units and resource planning units and manufacturing execution system provide the data layer. In fact, this is better called the physical layer of the system, where the real machines are there. And the integration layer, as I have shown you, the integration layer between this is a physical layer and this is a digital layer, and this is actually the integration layer that is integrating, which involves the network primarily, as well as the communication system over the network. Now comes the services layer. So as I mentioned earlier, there are different services, and these services are actually in this digital part of this layer, where the production integration or manufacturing or simulation services. And for each of these service, you can actually do some sort of simulation on the respective versions of the digital twin. Digital twins can be copied. Okay, with the digital twins copying, you can try different things at a different copy of that, and you will be able to do a lot of optimization operations simultaneously and find out what works best in a very short time. Okay, so you want to do, for example, you have a digital twin. This is a digital twin, and you have a copy C1, copy C2, and copy CN. Each one is actually a copy of this digital twin, and you can actually process or try out some new operation here in parallel to some other operation here and yet another operation here. So you will be able to do a lot of operations in parallel over individual copies of the digital twin. So you will be able to see what's the best decision, best action, or best process that can be tried in the physical world in a very short time. So that is why this makes real sense in cost optimization of large scale industries. And then at the higher layer, you have the business processes and the business layer to make business decisions. In some cases, the digital twins can be deterministic digital twins, okay, which means the operation is in deterministic region. If you consider the analysis, what if analysis can be done in single values. So for example, if you have a pressure is a function of temperature kind of relationship. So if this is actually linearly related or deterministically related, then it's very easy to find what if the temperature is X, how will be the pressure. Okay, this leads to a very simple single value, and it's easy to take such a decisions. But that is not the case in most of the real world cases, where there's a stochastic character involved, where there is probability representations or probability relationship may exist, or the relationship between P and B or Y and X may be probabilistically related. So in that case, so you may want to take decisions based on what is it called the probability distribution functions, rather than single value scenarios. Now let me just show one picture that is relevant for the next few minutes of this lecture, that is digital twins for healthcare. Okay, so as I mentioned earlier, the Internet of Things concept has several applications. One very important application, which is still not the biggest application, that is Internet of Medical Things. So Internet of Medical Things is actually applying the concept of IoT to healthcare domain. Okay, there are so many advantages in that. As I have shown you earlier, this is still a single-digit percentage of the whole IoT activity now, but over the years, this is expected to be growing as a major segment too. Okay, now the conceptually, so you have patient here. Now we are all patients at some point of time, or will be at some point of time. At some point of time, you will actually have these kind of sensors attached to that. Even today, many of us are getting attached to the sensors. So they measure the body, vital signs or other non-vital signs of your body, and that makes raw data to the system. And this raw data gets repositorized in some hospital-based raw data database, which gets cleaned up undergoes pre-processing, and then represented in such a way that it can be undergoing machine learning or data analytics before the refined information is stored in the result database. Parallelly, you will also undertake your observations under physicians or nurses or other healthcare workers. So they will give you their inputs. Okay, they can give inputs like your eyesight may be poor, or your eyes are colored yellow, or you appear to be weak, and so on. Their input also as going as an input to the system. And then you have lab test data, some of the pathological results from lab data that also goes into the system. Okay, so that way a variety of input data streams, or maybe your bathroom will be reporting some historical body mass index to the system. Okay, bathroom was measuring you every day, and it actually gave some information that actually went into this, show how historically you have grown in your weight or your size or whatever. So that gets into this result database, and from this result database a digital twin is actually created for you. So this is actually a digital representation of a human being by the availability of the biomedical parameters, by the physiological parameters, by the biochemical parameters, and so on. So this digital representation will be used to treat you for your diseases, curing, or even treat, develop drugs for diseases, and so on. So it is also possible that you may have similarity between yourself and maybe other patients in the whole country. And that way, by comparing similarities between digital twins, so you may be able to compare similar case patients. And this similar case patients can be very significant. Maybe you have same problem as somebody else in another district. Maybe a cure that works for you might work for him or might for her too. So that way, similar case patients can be identified, similar case diseases can be identified, similar case cures can be used for this particular scenario. So this is one of the very rapidly evolving research fields in this area. So I will now focus on a few other areas very briefly. Digital twin network, where digital twin systems can actually communicate among themselves. This is an example, a virtual system which is a digital twin of a physical system. There is communication. As I mentioned earlier, actuation decisions go and sensing information goes this way. Okay, but if you have several such digital twins, there can be a situation of communication between digital twins as well as the physical thing. So this particular case, there's a virtual twin, a digital twin works with several physical things, which will give you some one-to-many control or actuation functions. But more important thing is actually this digital twin network, where you have several physical things. This is actually machine 1, this is machine 2, machine 3, and machine 4. And for example, for this, you have digital twin 1, digital twin 2, digital twin 3, and digital twin 4. And when there's an interaction between the virtual and the physical partners, but there is also an interaction possible, because the physical world they work with it, so in the virtual world also they should work with it. So any information that you might, any product that you send from M1 to M2, you should have some sort of a representative information that can happen from D1 to D2 too. So there is communication, many communication or information pass we can do. So there is also a communication between physical to virtual and virtual to virtual communication. So this is a representation of the digital twin for communication networks, where you have a virtual world with the cloud edge, and the real virtual representation of the elements of the physical world. In the physical world, you have devices, base stations, access points, and so on. And so your corresponding virtual entity will communicate with your physical entity. So this is a physical to virtual communication. and this is again a physical to virtual communication. And you also have virtual to virtual communications to represent the physical to physical communication on the ground. Okay, because in the ground, when you have a vehicle which is physically represented as a car communicating with a particular access point or something, then that physical communication which is actually happening in the real ground may be replicated or represented in the virtual world too. Okay. Now, let me just focus on the last topic that I want to mention here about the digital twins network for biomedical or Internet of Medical Things. The reason what I mentioned this is because it's one of the very, very hot, very early stage research. It also probably a revolution in the medical scenario. Also one of the important directions of growth for IoT. Okay, so I have already mentioned about the Internet of Medical Things architecture for digital twins, where a human representation is actually made. So this human representation or a digital twin of a human being actually made, which is actually not an easy process. Okay, this is actually a creation of a lifelong process. A personalized physiological model is updated with each input system, which means, as I mentioned, your smartphone will give some data, your physician will give some data, your laboratory scans will give some data. Any examination that you do, that will be giving some data which you might want to create or update in your digital twin. So your digital twin will get expanded with the details. So any scan you do, that will go into collecting information about your digital twin or updating your digital twin. Any operations that you do, that will go into the digital twin. Any heart related observations, heart performance related thing, any heart pacemaker, imagine that you installed a pacemaker, then that is actually going into your model or your digital twin. This is actually digital twin representation in the form of a complex AI network. And this information, all this information will eventually go in refining the digital or updating the digital twin representation of a human being. Okay. Now, there are three ways how digital health twins can be created. One is an AI-based approach. As I mentioned earlier, you have many relationships between your parameters. For example, how this, for example, complex relationship between physical parameters. Okay. For example, exercise to heart conditions and so on. Heart conditions, and there are so many other factors, including that of social network persons. If you are related to social networks, say that if you have somebody who is obese, okay, this is an obese person with the body mass index greater than 45, then there is a certain chance that you are also having a body mass index in the borderline or obese. So there is a 3 degree of influence in the social network that you may be able to see. So this is an information that is very useful for building your proximity to obese people. So you are likely to be obese too. Okay, that is likely to create a representation in the AI-based model of your digital health part. So in addition to that, there is a cyber physical systems approach that you do. So this cyber physical approach is actually using control system model or robotics model to create the relationship between entities or information modules for building your digital health twin. Okay, so then there's a third model called complex networks approach. This is actually using biochemistry or biomedical parameters, or this is actually using what is called a network medicine approach. Okay, biomedical or biochemistry or using the pathological networks of human body to create this network. Okay, now one technique is not enough. That's what the point I'm trying to say. This is a very, very complex application of IoT, and one type of network, one type of information is not enough to create multiple different very complex types of information is required to create a digital health twin for a human being for an IoT system. Now, I want to just point out one or two examples because this is going to take a lot of time and you may run out of time. So let me tell you this particular area called the network medicine that is becoming relevant as an digital twin for healthcare. Okay, so you actually create a network model of a person because the cellular modules are cellular interconnectedness or their influence on disease progression could lead to identification of disease genes and disease pathways, and it can be used for drug development. Okay, so what that means is you model the biological parameters of your body as a network involving different types of individual networks like protein interaction network, metabolic network, or regulatory network, or RNA networks. And such a similar biomedical networks or biochemical networks can be brought together to identify the a human biological network. Okay, so this is one such a network representation where it's called a diseasome. This is like a disease phenome, which means a disease visual observation of a disease such as a breast control, which is a disease, breast cancer, or pancreatic cancer, or tumors of various kinds. But our study in the biomedical engineering tells that certain disease genomes are directly related to these diseases. So, for example, for this breast cancer disease, there are genomes like BRCA1 or even BRIP1 and so on related. So there is large number of disease genomes that are said to be present from this presently causing or may have an association with the breast cancer. So the size of this disease is actually higher here. Now, this is actually a representation called bipartite network. Okay, so this bipartite network has a specific characteristics that you have two types of nodes in this. Okay, one set of nodes is set A, we can say. The other type of node set B, we can say. There are interconnections or edges between set A and B, but there are no edges between the members of set B or between the centers of set A. So that is what a bipartite graph is. Once you have modeled after doing a lot of biomedical experiments this network, you will be able to do analysis of this network to derive what is it called, a human disease network. So this human disease network is finding the relationship between diseases. For example, this breast cancer and prostate cancer as related in a very significant way because there are multiple genomes that are associated with individually, and there are certain genomes which are common for both. And this, since there are many genomes that are common for this, there is a likelihood that these two diseases are very close, and a person with this disease X may have a chance to contract disease Y too. Okay, so that way you will be able to develop this is human disease network which can be different for every human being. Okay, so what that means is you will be able to identify a larger, very complex human disease network by the biochemical analysis of a person or genetic analysis of a person itself, or because that you are related to somebody in the social network biologically, and your human disease network is now getting richer with that information. If they have problem with the deafness, there is certain chance that you also inherit the genes, you also have the problem with the deafness. Or if they have problem with a certain disease, then there is a possibility that you inherit certain qualities, and your social network tells you that your genome network, your disease network will have similarity and so on. So, in fact, there have been a lot of research done individually, and that is now getting into the digital twins applications, okay, of this huge network where the color represents related diseases, size represents the number of other diseases that are related, and there are certain diseases which are not really connected with that. So this is actually the single big connected network, which is called a giant component of this network, which the interconnection between diseases so on for a particular person. Okay, so out of these 1200 diseases, 867 have at least one link to other disorders, and 516 disorders form a giant component, suggesting that there is certain genetic origins of most diseases and they are shared with other diseases too. So once we have identified this network for human being, for a person disease network, you will be able to identify methods to break it. Okay, so the reason how that can be done is, so there are certain interactome is actually a network formed by the protein interaction or cellular interactions, and there are certain disease pathways that can be identified. So this third one is actually disease pathway, which is present for a person with a certain disease, and this is for another disease. And once you have identified the disease pathways, you will be able to identify where these essential pathways as well as disease pathways are present, and you will be able to solve that. So for example, this is a interactome for the network topology of the interactome, where there are certain functional modules that are present in this particular way, and the disease pathway is actually present in a different way. So you can decide which node in this can be broken so that you can affect the disease, you can avoid contracting the disease, and that treatment can be done in the genetic manner. Now, when it comes to that solution, so you create what is it called a digital replica of a human being. Okay, so this digital replica of a human being will involve biochemical network, protein network, your social network information, then your genetic analysis network, then your doctor's feedback, even the pathological test reports, then even you have this, what is it called, the observations from AI modules, and so on. So this digital representation is actually present in the data center, might be owned by a company, managed by a company or government or whatever. So as a patient, when you get a particular problem like the knee pain here, okay, so this digital replica will be showing up that pain. Okay, either through a report or through a pathological analysis or through a genetic model, say that you are likely to have this problem or you have this problem. And that then what happens is a replica of your digital twin is made. So this is your digital twin, 1, DT1, 2, 3, 4, and so on. Infinite copies of these are made, infinite replicas are made, and you try various cures. This is actually medicine 1, medicine 2, and medicine 3, and so on. Medicine infinity are tried for different copies or different replica of your digital twin, and one medicine works. So this medicine works for your cure. So remember, this is trialed, this is experimented in the computer domain itself. So this is called a computational, clinical trial or clinical trial or cure or computational medicine. Okay, so you actually do the experiment on a computational model of your body by making several hundreds or millions of replicas, and in a very short time you find a possible medicine that can cure your problem, and this problem is actually given as a true medicine for the patient to do. So this cure can actually be tried for other patients who might be facing similar problems by doing the similarity analysis across digital twins of various individuals. Maybe everybody except a couple of people in your family may benefit for this, because these medicines are highly personalized medicine. Okay, these are highly personalized in the sense that a cure that works for your knee pain may not be the one that works for your family member. So the allergy medicine that works for your case is not necessarily the solution that works for your immediate family member. So that way, this gives the highly personalized medicine world for you. So that's the reason why it is becoming very important to understand the possibilities opened up by this industrial revolutions, and particularly this industrial revolution 4.0. So the central part of the industrial revolution 4.0 is actually the internet enabled things, where including human beings are actually getting internet enabled, And we have also seen architectures for Internet of Things, and the most recent direction of representing very complex systems as a digital representation or digital replica in the form of digital twin. And we have looked at how the digital twins for the healthcare or Internet of medical things are actually developed. So here with this, let me conclude that talk. If you have any questions, feel free to ask me now.
Now we have a short question and answer session. Participants, please raise your questions.
So I'll stop sharing so I can see this chat box. If you have any questions on the chat box.
Yes, sir, there are some questions.
Okay, so let me see. Anupam Tiwari's question, let me take first. Organizers good show. Yeah, okay, 5 questions. I have sent my previous presentation yesterday. If you can get it, so this I'll send today. Okay, so yeah, so Anupam Tiwari has reliability and maintainability is a big issue in IoT. That's very, very true, because these things are very low energy consuming, very small form factor, very limited in terms of resource capabilities. So reliability is an issue, and maintainability is also an issue. But over time things will improve. When real companies invest sufficient amount of money, you can get highly miniaturized and highly reliable devices. So for now, this is that's what I'm saying. This is a growing phase. A lot of uncertainties, lot of incompleteness, and lot of issues are there. But over time, it will become very reliable, no doubt about it. Standardization is actually happening now. As I mentioned earlier, IEEE has come up with an architectural standard. IEEE is also working on other standards. For example, I am a member of a working group for standardizing blockchains for IoT. In fact, in this particular aspect of blockchain itself, there are 3 standardization events, one going in the European Union, another by IEEE, and then even Chinese government is trying to have a standardization for IoT and blockchains too. So that is now happening. As I mentioned earlier, I'm a working member group. Many other IEEE volunteers are working member group too. So it is not fixed. It is happening now. This 2019 standard will get evolved to other matters where there are no standards existing, to other areas where the standards are not existing. So it's not yet fixed. Can we make digital twin of anything without a mathematical model? No. Mathematical model is very, very important. But that alone is not enough, because you need control system models, you need to have AI models, you need to have sometimes biomedical models. Okay, that's the reason I mentioned, because we are making digitization of very, very complex physical things, one kind of or simple kind of models will not be enough. But still, mathematical model is one of the very, very important things. I have building and now feeding data of building maintenance, etc. Can we say it's a digital twin? It can be said as a digital twin, but it's a very crude, very early stage digital twin. But if you have expanded the capability to have smart windows, smart doors, smart walls, and even the structural elements, if you attach a sensor to every joint of the building, then it actually builds how the stress and strain develops within the building at a different time of a day or year or whatever. Then you are actually enhancing the capability. Okay, so you are actually building towards creating a digital twin of the building, but you are in a very, very early stage. So if we have my health data every year, can I make a digital twin of my? Yeah, yes. Again, as I mentioned earlier, we are in a very early stage in the case of digital twin. I feel there's a real need for us to create a history of our medical data, which will be very much useful for us individually as well as for our doctors. Okay, that's very, very important to do that, and it will definitely come into existence. So otherwise, there are no further questions. If you have any other question now, please feel free to ask me in the next 1 minute. Okay, thank you all for coming and listening to me. I'm very glad that Dr. Anil Kumar had invited me for interacting with you. If you have any questions, feel free to email at this email address, bsmanoj@itl.org. If you need any kind of advice or help on choosing research topics or guiding students, feel free to get in touch with me in this area. Okay. Okay, then if there are no further things, I would like to close the session.
Sir, on behalf of the institution and participants, I express our gratitude to you, sir, for
Okay.
delivering the very interesting and informative session on IoT. Thank you, sir.
Yeah, thank you, madam. Thank you all. Thank you, Professor Anil Kumar. Bye.
Participants' feedback form will be shared in WhatsApp group. And next session will start at 11:15. The session is on live in harmony with nature.
Madam, feedback link is not opening.